A civilization could one day use entire galaxies as power plants. This is the realm of a Type 3 civilization, an entity of such staggering power it treats stars as mere batteries. By the end of this exploration, you will understand the actual physics and engineering that could make this possible, from stellar mines to black hole generators. We will see how a society might move from gazing at the heavens to literally holding them in its hands, bending the light of billions of suns to its will. What does it truly mean for intelligence to master a galaxy? The scale itself is a simple yet profound thought experiment. It asks a single question: how much energy can a society command? The answer places that society on a cosmic map. At the very bottom, before even Type 1, we find our own current status. We are still a 0.7 civilization. We tap into fossil fuels, nuclear fission, and sunlight, but we do not yet control the full energy budget of our planet. We are like a child who has learned to light a candle but cannot yet build a fireplace. A true Type 1 civilization would have no energy scarcity. It could control its planet's weather, stabilize its geology, and power a global technological society without strain. Every watt of sunlight that strikes the Earth, every gust of wind, every geothermal pulse would be at its fingertips. It is a world of absolute planetary mastery. The leap to Type 2 is where the scale truly enters the realm of the astronomical. This civilization does not just live on a planet orbiting a star. It lives with its star. It has built a structure, perhaps a vast swarm of orbiting collectors known as a Dyson sphere, to capture every single photon of light its sun produces. Its entire industrial base, its computational networks, its very way of life would be powered by the steady, immense fusion reactor at the center of its solar system. This is no longer planetary engineering, it is stellar engineering. The civilization becomes a permanent, inseparable partner to its star, a custodian of a solar furnace. And then we arrive at Type 3. The numbers involved here cease to be merely large. They become almost philosophical. Our galaxy, the Milky Way, is home to somewhere between 100 billion and 400 billion stars. A Type 3 civilization commands the energy output of all of them. It is not about building one Dyson sphere. It is about building billions of them, or something even more efficient, across a volume of space so vast that light itself takes over 100,000 years to cross from one end to the other. This is the scale that transforms a civilization into something we might struggle to recognize as a society at all. Its concerns, its projects, its very sense of time would be galactic. It would think in terms of star clusters and spiral arms, its history measured in millions of years, its energy budget drawn from a river of power so wide it could drown 1,000,000 suns. This framework sets the stage, but it raises an even more pressing question. How, what machines, what principles of physics could possibly allow for the harvesting of an entire galaxy? The true magnitude of this power is found in the numbers. A typical spiral galaxy, like our own Milky Way, contains over 100 billion stars. Their combined light output is staggering, on the order of 10 billion times the luminosity of our Sun. Every second, this galactic heart pumps out more energy than our star will produce in its entire 10 billion-year lifetime. Yet this radiant light, this visible glow, is merely the starting point. A galaxy is a vault of energy in many forms. There is the immense gravitational potential energy locked within the orbits of stars, a cosmic pendulum that could be tapped. There is the kinetic energy of vast, swirling clouds of gas and dust, moving at incredible speeds. There is the unfathomable power sleeping in the supermassive black hole at the galaxy's core, a gravitational well of almost infinite depth. And then there is the mysterious, dominant presence of dark energy, woven into the fabric of space itself. To put this total budget into a human perspective, consider all the energy our species has ever used. From the first controlled fire through the Industrial Revolution to every power plant and solar panel operating today, the sum total of human energy consumption is a single, tiny drop. The energy budget of a galaxy is an ocean that could drown 1 billion planets. A Type 3 civilization would operate on a scale trillions upon trillions of times greater than everything we have ever accomplished. Numbers this large cease to be practical. They become a new kind of mathematics, a language for describing the ambitions of gods. This sheer magnitude is not just a fun fact. It is the fundamental constraint that dictates everything. You cannot manage a galactic energy grid with planetary thinking. The very tools, the very projects, must be conceived on a scale where a star is a manageable unit and a nebula is a convenient reservoir. It forces a perspective shift so profound it changes what a civilization even is. To grasp this scale, we must start with a single, brilliant point of light. Our own sun pours out enough energy every second to power our current civilization for over 500,000 years. A Type 2 civilization would not let a single photon of that light escape into the void. It would construct a Dyson swarm, a vast constellation of orbiting solar collectors, each one a continent-sized platform covered in photovoltaic cells or mirrors. These collectors would beam the harvested energy, perhaps as concentrated microwaves or lasers, to wherever it is needed within the solar system. This is not a solid shell, but a dynamic, living network, a technological hive buzzing around its star. For a civilization that has achieved this, its home star becomes a reliable, steady battery, a foundation for projects we can barely dream of, but this is only the first step. A single Dyson swarm is a monumental achievement. A Type 3 civilization, however, would need billions of them. Imagine looking out at the Milky Way from a distant vantage point. Every star you see, from the brilliant blue giants to the steady yellow suns like our own, would be surrounded by a faint, intricate shimmer, a telltale signature of captured light. The galaxy would no longer shine with its natural, fiery glow, but with the purposeful, structured luminescence of intelligence at work. The logistics are beyond human comprehension. Building one Dyson swarm around one star is a project spanning centuries, requiring the dismantling of planets for raw materials and the coordination of unimaginable numbers of autonomous machines. To replicate this process across the galaxy, the civilization would need something far more powerful than construction crews. It would need self-replicating probes, often called von Neumann probes. These would be robotic architects dispatched to a target star system. Upon arrival, a single probe would use local resources, asteroids and comets and dust to build copies of itself. Those copies would then fan out to build the energy collectors, and then move on to the next star, creating an exponential wave of construction that spreads from star to star like a gentle, purposeful tide. This is not a project managed from a central office. It is an idea set in motion, a set of instructions unleashed into the cosmos that builds the necessary infrastructure automatically over millions of years. The energy harvested from each star would not just power local projects. It would be fed into a galactic scale power grid. But how do you transmit energy across the unimaginable gulfs between stars? You cannot string wires through interstellar space. The solution might lie in beaming energy as tightly focused lasers, or perhaps by using the fabric of spacetime itself. Some theoretical concepts suggest that a sufficiently advanced civilization could create stable wormholes, not for travel, but as conduits for power, creating a direct pipeline between a star and a distant consumption point. Others propose converting the energy into a more fundamental form, like mass, shipping it as compact packets of matter to be reconverted at the destination. Each Dyson swarm becomes a power station on this grid, and the civilization itself becomes the grid, a nervous system of energy and information woven through the spiral arms. This vast, silent network of captured suns is the first foundational layer of galactic mastery. It provides the steady, immense power required for the next, even more profound phase of engineering, where the civilization moves from harvesting stars to manipulating the very architecture of the galaxy. But capturing a star's light is only the beginning of its potential. A truly advanced civilization would not just sip from the surface, it would tap the source directly, engaging in a practice we might call star mining. This is the concept of stellar lifting, and it transforms a sun from a simple lamp into a deep, renewable well. The principle is audacious yet grounded in known physics. A star is a vast, churning sphere of plasma, primarily hydrogen and helium, fusing under immense pressure. Stellar lifting proposes using technology on a staggering scale to gently skim this material away. One method could involve deploying a network of colossal magnetic fields, like a cosmic fishing net, to guide streams of superheated plasma away from the star's corona. Another might use incredibly focused beams of energy to push material into a controlled outflow. The siphoned plasma, this raw star stuff, would then be collected by orbiting facilities. The purpose is twofold. First, it provides an unimaginably vast supply of fusion fuel. This hydrogen and helium could power the civilization's own fusion reactors elsewhere, or be used in even more advanced energy schemes. Second, and perhaps more fascinating, this process can actually extend the star's life. A star's lifespan and behavior are dictated by its mass. A heavier star burns its fuel faster and dies younger, often in a violent supernova. By carefully, slowly reducing a star's mass through stellar lifting, the civilization can slow down its internal fusion reactions. It effectively turns a raging, short-lived giant into a calmer, longer-lived, more stable furnace. This is not just energy harvesting, it is stellar husbandry. A Type 3 civilization would think in terms of managing entire stellar populations. It could identify massive, unstable stars destined for cataclysmic supernova and gently reduce their mass over millennia, preventing explosions that would sterilize entire sectors of space and vaporize precious infrastructure. It might even attempt to reignite the cores of dying, cooling stars by injecting fresh fuel or manipulating their internal dynamics. In this view, the galaxy becomes a vast garden, and the civilization its meticulous gardener. It prunes the dangerous branches, nourishes the fading plants, and cultivates the entire ecosystem for long-term, sustainable yield. This represents a fundamental shift from passive collection to active, intelligent management of astrophysical processes. It is the moment a civilization stops being a tenant of the galaxy and starts becoming its architect. Yet the ultimate energy source may not be found in the light of stars, but in the profound darkness at the galaxy's very heart. A supermassive black hole, like Sagittarius, a star at the center of our own Milky Way, is often seen as a cosmic predator, a devourer of light. For a Type 3 civilization, however, it would be seen as the most powerful dynamo in existence. The key lies not in the black hole's event horizon, the point of no return, but in the chaotic, energetic region just outside it. This is the ergosphere, a zone of twisted spacetime where the black hole's immense rotation drags the very fabric of the universe around with it. Here, physics allows for a remarkable trick known as the Penrose Process. Imagine a civilization that could drop a package of matter into this ergosphere. The intense rotational energy of the black hole could split that package in two. One piece falls past the event horizon, lost forever, but the other piece is flung back out, robbed of negative energy and carrying with it more kinetic energy than the original package had when it went in. It is like stealing spin from a cosmic top. The civilization has effectively extracted rotational energy directly from the black hole itself, slowing it down minutely in the process. This is not science fiction. It is a valid prediction of Einstein's theory of general relativity, but an even more powerful method might involve not stealing spin but feeding the beast. By carefully directing a stream of matter, perhaps gas from a controlled stellar wind or even asteroids, into the black hole's gravitational grip, a civilization could create a managed accretion disk. This disk, a swirling maelstrom of superheated plasma, would blaze with the heat of millions of suns as friction and magnetic forces convert gravitational energy into radiation. It would be a furnace built around a bottomless pit, with the civilization acting as the stoker, controlling the fuel feed to regulate the power output. The most speculative and potentially most powerful concept of all is known as a black hole bomb or superradiance. This involves surrounding a rotating black hole with a gigantic reflective sphere. Light or other radiation, once trapped in the ergosphere, would bounce between this mirror and the black hole's twisted spacetime. With each pass, the black hole's rotation would impart more energy to the light, amplifying it exponentially, like sound waves building in a resonant chamber. The sphere would then harvest this amplified energy. In theory, such a device could convert a significant portion of a black hole's mass into usable power over time. Tapping a supermassive black hole would provide something a Dyson swarm cannot: a centralized, ultra-dense, and incredibly stable anchor for the entire galactic energy grid. While starlight is harvested across billions of points, the black hole offers a single titanic generator, a gravitational cornerstone for a civilization's power architecture. It represents the pinnacle of cosmic engineering, turning the most destructive object in nature into the ultimate engine of creation. These megastructures would not simply exist within the galaxy. They would become the galaxy's new skeleton. The ultimate expression of a Type 3 civilization's power is not just in harvesting energy, but in reshaping the cosmic landscape itself to make that harvest perfect. This leads to concepts so vast they bend our understanding of engineering. Imagine a single titanic ring encircling the entire galactic disk, positioned far out in the calm of the galactic halo. This circumgalactic ring would be a band of linked energy collectors, each segment capturing the combined starlight from billions of suns shining up from the galactic plane below. It would be like building a solar panel the size of a galaxy, turning the entire luminous disk into a unified power source. The scale is incomprehensible, requiring the mass of millions of stars to construct, but for a civilization commanding such resources, it offers a singular, stable platform for energy capture on a truly unified scale. The logistics of building something so immense lead to an even more dynamic idea, the Ashkadov thruster, but applied to an entire population of stars. A standard Ashkadov thruster is a stellar engine, a colossal parabolic mirror built around a single star. The star's own radiation pressure pushes against this mirror, creating thrust and slowly, over millions of years, moving the star through space. Now amplify this concept across the galactic stage. A Type 3 civilization would not see stars as fixed points of light. It would see them as movable assets. By equipping vast swaths of its stellar population with such engines, it could begin a grand project of galactic orchestration. It might gently herd stars into more efficient clusters for easier energy collection, or clear chaotic regions of space to create stable zones for its most delicate experiments. Over epochs, this meticulous stellar shepherding could even alter the galaxy's rotation or its trajectory through intergalactic space. The civilization becomes a cosmic conductor, directing the symphony of stellar motions. This level of control hints at the final, almost philosophical transformation. At this apex of development, the line between the civilization's infrastructure and the galaxy's natural architecture begins to blur and then vanish entirely. The Dyson swarms become a new kind of nebula, glowing with structured light. the energy transmission conduits threading between stars mimic the filaments of cosmic web. The managed black hole at the center pulses like a regulated heart. The galaxy itself is no longer a wild, natural system. It is a garden that has been tended, a machine that has been built, a work of art that has been completed. The civilization and its home galaxy become a single, integrated entity, a hybrid of mind and matter operating on a scale that dwarfs time. This raises a profound and haunting question for us, looking up at the silent, spiraling stars. If such a civilization is possible, and if its signature would be the transformation of a galaxy's very structure and light, then we must ask ourselves, what are we actually seeing when we peer into the depths of space? The silent starlight of a Dyson swarm is useless if it cannot reach the civilization that needs it. This is the paramount logistical challenge of a galactic empire, moving power across the unimaginable voids where even light takes years, centuries, or millennia to travel. A star's energy, harvested in one lonely corner of a spiral arm, must somehow find its way to a construction project in another, or to the hungry computational networks near the galactic core. The solution cannot be wires, it must be something that rides on the fabric of space itself. The most plausible candidate is the directed energy beam, a river of photons so perfectly focused it barely spreads over its epic journey. Imagine a civilization constructing colossal laser arrays orbiting its managed stars. These would not be weapons, but the most precise power transmission lines ever conceived. Each beam, composed of microwaves or optical light, would be aimed with astronomical precision at a relay station light years away. That station, a lonely outpost floating in the deep dark, would capture the beam, use a fraction of its power to sustain itself, and then refocus and retransmit the energy toward the next node in the chain. This creates a network of energetic stepping stones across the galaxy, a circulatory system of light connecting every power source to every point of consumption. The engineering demands are almost beyond description. These beams must maintain their coherence over distances where a target the size of a solar system appears as a tiny, trembling dot. The relay stations must maintain their alignment for millennia, compensating for the subtle gravitational tugs of passing stars and the slow drift of galactic orbits. A single miscalculation, a relay failing after 10,000 years of flawless operation, could send a beam of star-level power slicing through an inhabited solar system or missing its target entirely, wasting eons of collected energy. This network would be the civilization's greatest and most vulnerable achievement, a web of light so delicate and so vast it defines the structure of their realm. Yet some theories suggest there might be a shortcut, a way to bypass the slow crawl of light-speed transmission entirely. This is where physics brushes against the edge of science fiction, in the strange phenomenon of quantum entanglement. When two particles become entangled, their properties are linked instantaneously, no matter the distance separating them. Change the state of one, and the other changes in the same instant, seemingly communicating faster than light. Could this be used for energy transmission? The tantalizing answer is not in the way we might hope. You cannot send power itself through entanglement. You cannot make energy magically appear across the galaxy, but you could, in theory, send the perfect instructions for its use. Imagine an entangled pair of particles, one kept at a power station orbiting a star, and the other at a distant city needing energy. By carefully manipulating the particle at the star, the engineers could force its entangled twin at the city into a specific, known state. That state change could act as a flawless, instantaneous signal, a command that tells the city's local power grid to tap into a pre-positioned energy reserve at the exact same moment the star's energy is being diverted into storage. It would be the ultimate coordination tool, allowing for perfect synchronization of energy use across light years, creating a unified heartbeat for a civilization spread across billions of stars. Whether through beams of light or quantum whispers, this transmission infrastructure does more than move power. It transforms the galaxy's very nature. A collection of isolated, brilliant stars becomes an interconnected grid, a single vast machine. Energy harvested from a young blue giant in the Perseus arm can fuel a computation hub in the Orion spur. Resources mined in one nebula can be processed using power beamed from a star cluster on the far side of the galactic core. This connectivity enables the civilization's grandest projects, allowing it to act as one coherent mind across hundreds of thousands of light years. The galaxy ceases to be a place they live in. It becomes a circuit they have completed, a thought they are thinking, alive with the purposeful flow of power and information. But even a galaxy transformed into a luminous engine is still only a fraction of the story. All the stars, planets, and swirling gas we can see or detect make up a mere 5% of what is actually out there. The overwhelming majority of the cosmos is made of things we cannot see: dark matter and dark energy, the twin shadows that shape the universe. For a Type 3 civilization, mastering the luminous 5% would be just the first chapter. The final, almost unimaginable frontier would be learning to touch and use that other 95%. This is the leap from engineering matter to engineering reality itself. Dark matter is the universe's hidden scaffolding. We know it exists because we can see its gravitational grip on galaxies, holding them together as they spin at speeds that should fling stars into the void. It is a ghostly substance that does not emit, absorb, or reflect light, yet it outweighs all the normal atoms in the cosmos by a factor of about 5 to 1. For a civilization that has harnessed stars, dark matter represents the ultimate untapped resource. But how do you harvest something you cannot even see or touch in any conventional way? The answer lies not in capturing the dark matter particle itself, which may be nearly impossible, but in manipulating the gravitational wells it creates. Think of a galaxy not as a flat disk of stars, but as a deep, invisible gravitational valley carved primarily by dark matter. A star is a small hill within that valley. A sufficiently advanced civilization might learn to tap the gravitational potential of the entire valley. One speculative method could involve placing immense, dynamic structures at strategic points within the galaxy's dark matter halo. As these structures orbit, they could move through the changing gravitational gradients, converting that motion into usable power, like a turbine in an invisible river of gravity. It would be a form of cosmic geoengineering, but on a scale where the geo is the fabric of spacetime shaped by unseen mass. Then there is dark energy, an even more profound mystery. This is not matter at all, but a property of empty space itself, causing the very expansion of the universe to accelerate. It acts as a kind of anti-gravity, pushing galaxies apart. If dark matter is the hidden scaffolding, dark energy is the hidden engine of expansion. Harnessing it seems like a paradox. How do you extract energy from the vacuum of space as it stretches? The theories here are at the very edge of theoretical physics, but they point to a staggering possibility. If a civilization could somehow create a localized region where the effects of dark energy are concentrated or reversed, it might create a perpetual source of negative pressure, a wellspring of cosmic repulsion. In essence, they would be learning to bottle the force that drives the universe apart. The energy density of dark energy is incredibly small everywhere, but the total amount across cosmic volumes is colossal. Mastering it would mean moving beyond harvesting things within space to harvesting the properties of space. Achieving this would mark the final transition. A civilization that begins by capturing sunlight, then moves to shepherding stars and tapping black holes, is a master of the visible cosmos, but one that learns to interact with dark matter and dark energy ceases to be an engineer of objects. It becomes an architect of the underlying framework. It would not just live in the universe, it would begin to converse with the fundamental rules that wrote it. This is no longer about building bigger power plants. It is about learning to read and rewrite the source code of reality. The energy from this mastery would be billions of times greater than everything luminous in the galaxy combined, offering power for projects so vast they defy our current language to describe them. Projects that might not be about consumption at all, but about creation on a cosmic scale or communication across the multiverse. It forces us to ask a humbling question. When we look at the silent, dark spaces between galaxies, are we looking at an empty void, or are we looking at the future fuel for intelligences we cannot yet comprehend? This staggering power must ultimately serve a purpose. What could a civilization possibly do with the energy output of billions of suns? One profound answer lies not in building bigger machines, but in building a deeper kind of mind. The ultimate project for such a civilization might be the creation of a Matrioshka brain, a concept that transforms a star from a power source into a thinking engine. Imagine not just one Dyson sphere, but a series of them, nested like the layers of a Russian doll, each one capturing the waste heat from the layer inside. The innermost shell, blazing hot from the star's direct light, would run the fastest, most energy-intensive computations. The next layer out, cooler, would handle different processes, and so on, until the outermost shell radiates away the faint, leftover warmth into space. Every single joule of the star's energy would be put to work doing one thing: processing information. This is a computer built on the scale of a solar system, its processing power dwarfing every human thought that has ever occurred by an incalculable factor. For a Type 3 civilization, this concept scales up to a galactic level. You would not build just one, you would build billions, linking them into a single, galaxy-spanning computational network. Each star becomes a node in a cosmic neural net, a processor in a mind so vast its thoughts unfold over centuries and its memories span the lifetimes of species. The entire luminous output of the Milky Way would be channeled into a single, unimaginable act of contemplation. This shifts the very definition of a civilization's purpose. For us, energy powers industry, transportation, and comfort. For a civilization that has reached this stage, energy would fuel thought itself. The goal is no longer outward expansion, but inward exploration. What would such a super-intelligence think about? It might run hyper-detailed simulations of cosmic history, tracing every particle from the Big Bang forward to understand the precise conditions that led to its own existence. It could model every possible future, calculating the ultimate fate of the universe with perfect precision. It might dedicate eons to solving fundamental questions of mathematics and physics that are forever beyond our grasp, finding the elegant equations that truly govern reality. This represents a possible end state, a maturity where the physical universe has been mastered, and the final frontier is the realm of pure information and understanding. The civilization becomes less a society of beings and more a single, unified field of consciousness, a galaxy that has woken up to think about itself. All those Dyson swarms, those stellar engines, those black hole dynamos, would have one ultimate function: to power a single, sustained thought. This leads us to a haunting and beautiful possibility. When we look at the silent, structured galaxies in our telescopes, we might not be looking at abandoned engineering projects. We might be looking at galaxies that have finished building and have now turned inward, their light the steady glow of a universe in deep cosmic meditation. This vision of a galaxy in contemplation brings us to a practical yet equally profound question of cosmic resource management. A Type 3 civilization would not just accept the galaxy as it is. It would seek to improve it, to engineer its very structure for peak performance. This leads to a concept we might call star cluster optimization, treating the densest regions of space as integrated energy farms rather than random celestial gatherings. Galaxies are not uniformly sprinkled with stars. They contain incredibly dense knots known as globular clusters. ancient spheres that can pack hundreds of thousands of stars into a relatively tiny volume of space. To us, they are beautiful, glittering ornaments. To a galactic engineer, they represent both a challenge and an immense opportunity. The challenge is gravity. In such a tight, chaotic environment, stars can whip past each other at tremendous speeds, their orbits unstable over cosmic timescales. A close gravitational encounter could fling a star out of the cluster entirely, or, in a worst-case scenario, lead to a catastrophic collision. For a civilization that depends on every star as a power node, this natural volatility is unacceptable. It is like building your entire power grid on top of an earthquake fault. The solution is a project of staggering subtlety and scale, stellar shepherding on a cluster-wide level. The civilization would need to gently, precisely adjust the orbits of hundreds of thousands of individual suns. This would not be done with rockets, but with the application of immense, carefully calibrated forces, likely using the same network of Ashkadov thrusters or focused energy beams we discussed earlier. The goal would be to rearrange the stars into a stable, optimal configuration. Imagine transforming a wild, buzzing swarm of bees into a perfectly spaced hexagonal honeycomb. Each star would be positioned at an ideal distance from its neighbors, close enough to make energy collection and transmission efficient, but far enough apart to eliminate the risk of gravitational disruption for billions of years. The cluster would become a calm, orderly, and perfectly efficient power plant, its collective light output harnessed by a unified web of collectors. But optimization does not stop with managing existing stars. A truly advanced civilization would look at the vast, dark nebulae, the stellar nurseries where new stars are born, and see not just a natural process but a factory floor. They could learn to trigger star formation on demand. By using precisely aimed energy beams or the strategic collision of gas clouds, they could initiate the collapse of a nebula, guiding the birth of new stars with specific, desirable properties. They might cultivate stars that are stable, long-lived, and of an ideal mass for energy harvesting, essentially farming perfect solar furnaces. This turns the life cycle of stars from a random act of nature into a deliberate, industrial process. A nebula is no longer just a cloud, it is a cultivated field, and the stars that emerge from it are a planned crop, sown and harvested on timescales that dwarf human history. This level of environmental control represents a fundamental shift in a civilization's relationship with the cosmos. It is no longer about building structures within the galaxy. It is about treating the galaxy itself as a malleable system, a vast machine whose components can be tuned and optimized. Managing star clusters as integrated units demonstrates a mastery that goes beyond mere collection. It is active, sustained stewardship on a million-year timeline. The civilization ensures that its energy sources are not only abundant but also stable, efficient, and renewable across cosmic epochs. It is the difference between a hunter-gatherer who takes what the forest provides and a farmer who terraforms the landscape, plants specific seeds, and irrigates the fields to guarantee a bounty for generations to come. In this optimized galaxy, nothing is left to chance. Every nebula, every cluster, every solitary star has a purpose and a place within the grand design, all orchestrated to sustain a river of power so vast it could forge new realities. Such immense power carries an equally immense responsibility. The act of harvesting energy from a galaxy is not a passive one. It is a fundamental act of transformation, and every transformation has consequences. Wrapping a star in a Dyson swarm changes its light profile forever. Moving stars with colossal engines alters the gravitational dance of entire clusters. Even the most careful stellar mining could subtly change a sun's composition and radiation, potentially affecting any orbiting worlds. A civilization that has achieved this level of mastery must therefore ask itself a profound ethical question. In reshaping the cosmos to serve its needs, what else is it reshaping, and who else might call that cosmos home? This is the frontier of cosmic ecology, the idea that a galaxy is not just a resource depot, but a complex, interconnected system. A thoughtful Type 3 civilization would likely develop principles to guide its engineering, not out of weakness but out of profound wisdom. The primary concern would be the preservation of life in all its possible forms. Before converting a star into a power plant, they would conduct surveys of staggering detail, scanning every planet, moon, and asteroid in that system for any sign of biological or even pre-biological activity. A world showing the atmospheric signature of life, or a moon with a subsurface ocean, would be placed off limits. Its star would remain untouched, its light left to shine naturally, preserving the conditions for that life to continue its own independent story. This would not be a minor concession. It would mean deliberately foregoing the energy of millions, perhaps billions, of stars, solely to protect the possibility of other minds arising in the darkness. Beyond protecting existing life, such a civilization might also consider the potential for future life. They could designate vast regions of the galaxy as wilderness preserves, entire spiral arms or nebulae where no megastructures are built and no stars are moved. In these zones, natural processes would be allowed to proceed without interference. Stars would be born, live, and die in spectacular supernova, scattering the heavy elements needed for planets and life across space. New solar systems would form from the ashes of the old, each one a fresh roll of the cosmic dice for biology and consciousness. These preserves would serve as both a genetic and an intellectual bank for the galaxy, ensuring that the natural, unpredictable path of evolution continues alongside their own engineered order. This ethical framework transforms our image of a Type 3 civilization from a voracious consumer into a careful steward. It challenges the common dystopian science fiction narrative of a galaxy stripped bare by a relentless, expansionist empire. Instead, we might envision a civilization that sees its role not as a conqueror, but as a gardener or a librarian of the cosmos. Their greatest project would be one of balance, sustaining their own unimaginable complexity while nurturing the fragile, flickering sparks of life and potential scattered across the stars. Their legacy would not be a galaxy drained of light, but a galaxy carefully tended, its brilliance a mix of wild, natural suns and the purposeful, structured glow of intelligence at work. This perspective suggests that the ultimate sign of a truly advanced civilization may not be the scale of its machines, but the depth of its compassion and the breadth of its vision for a living universe. The silent glow of a galaxy might be the most profound message it could ever send. If a civilization has truly mastered its stellar home, reshaping its light and energy for its own purposes, then that galaxy should look fundamentally different from a natural one. This is the core idea behind the search for technosignatures, the detectable byproducts of technology on a cosmic scale. For a Type 3 civilization, these signatures would not be subtle. They would be painted across the entire galaxy, visible from billions of light years away. The most promising clue is a paradox of engineering, a signature of waste. A Dyson swarm does not make a star vanish. Instead, it captures the star's visible light and converts it into useful work. But the fundamental laws of thermodynamics dictate that no process is perfectly efficient. All that collected energy must eventually be re-radiated as waste heat. For a star wrapped in a Dyson swarm, this waste heat would emerge not as the star's original visible light, but as a much cooler, longer wavelength glow in the mid-infrared part of the spectrum. From our vantage point, a star like our Sun, if fully enclosed, would appear to dim in visible light and then blaze brilliantly in infrared. Now magnify this effect across 100 billion stars. An entire galaxy transformed by a Type 3 civilization would have a bizarre and unmistakable fingerprint. Its natural, fiery starlight would be dramatically reduced. In its place, the galaxy would shine with an intense, uniform infrared glow, the combined waste heat of a trillion engines. Astronomers already have the tools to look for this. By analyzing the full spectrum of light from distant galaxies, they can search for an excess of mid-infrared radiation that cannot be explained by natural processes like dust clouds warmed by young stars. A galaxy that shows this signature, a galaxy that is oddly dim in the visible universe but radiant in the infrared, would be a prime candidate for a cosmic engineer's workshop. But light is not the only messenger. The gravity of a megastructure is another telltale sign. Building something with the mass of a planet or even a star leaves a gravitational imprint. If a civilization is constructing massive orbital rings or moving stars with Skadov thrusters, the delicate orbital dance of celestial bodies in that system would be subtly perturbed. We could detect stars that wobble in ways that cannot be explained by the pull of unseen planets, their motions hinting at the presence of vast, artificial masses in precise orbits. On a galactic scale, the organized shepherding of stars into optimized clusters would create patterns of motion that defy natural models of galaxy formation and evolution. It would look less like a random swarm and more like a carefully choreographed ballet, with stars moving in synchronized, purposeful ways that gravity alone could not arrange. Perhaps the most deliberate signal of all would be modulation. A civilization might not just use its galactic scale power grid, it might communicate with it. They could intentionally pulse their energy beams or vary the output of their Dyson swarms in complex mathematical patterns. This would impose a rhythmic, artificial signature onto the very light of the galaxy, a kind of cosmic heartbeat encoded with information. From our perspective, the galaxy's overall brightness would flicker in a precise, repeating sequence, a beacon of intelligence so powerful it uses an entire island of stars as its signal lamp. Our searches for these signatures have already begun, though they scan a cosmos that remains quiet. Projects analyze vast catalogs of galaxy spectra, looking for that mysterious infrared excess. Others monitor the light curves of millions of stars for the unnatural dimming that might indicate a partially built megastructure passing in front of them. So far, the universe appears natural. We see no galaxies glowing with the structured warmth of a Dyson-filled empire, no stars dancing to an artificial rhythm. But this absence is not a closed door. It is a map. Each search that comes up empty refines our understanding of what galactic engineering truly entails, helping us distinguish between a science fiction fantasy and a plausible future for intelligence. It teaches us what to look for next, and in the grand silence, we are learning to listen for the footsteps of giants. The search for these cosmic signatures leads us to a more volatile, yet potentially more powerful form of energy. Beyond starlight and gravity lies a substance of pure potential, a mirror to everything we know. This is antimatter, and for a civilization mastering a galaxy, it represents the ultimate battery. Every particle of ordinary matter, like the protons and electrons that make up our world, has an antimatter counterpart with opposite charge. When matter and antimatter meet, they annihilate each other in a flash of pure energy. A conversion so complete it makes nuclear fusion look inefficient. This is not a theoretical dream. We create tiny amounts of antimatter in particle accelerators today, but the process uses far more energy than we get back. For a Type 3 civilization, this equation flips. With the power of billions of stars at their disposal, the cost of production becomes trivial compared to the payoff. They would not see antimatter as a laboratory curiosity, but as the premium fuel for their most demanding tasks. Imagine the need for a sudden, colossal burst of power, perhaps to initiate a star-forming event in a distant nebula or to execute a precise course correction for an entire star cluster. Firing up extra Dyson swarms would be too slow. Antimatter, stored in magnetic bottles, could provide that instantaneous titanic surge on command. It would be the civilization's emergency generator and its ultimate propulsion system, capable of accelerating starships or even small worlds to a significant fraction of light speed. But where would they get it? The universe in its natural state is almost entirely made of matter. Antimatter is exceedingly rare, but it is not absent. It is forged in the most violent places imaginable, around the frenetic jets of supermassive black holes, in the intense magnetic fields of spinning neutron stars called pulsars, and in the turbulent remnants of supernova explosions. Pairs of matter and antimatter particles are spontaneously created. A galactic civilization would identify these natural antimatter factories and build harvesting facilities around them. Vast magnetic scoops, like cosmic fishing nets, could sweep through the energetic regions around a magnetar, a neutron star with a magnetic field a quadrillion times stronger than Earth's, collecting the antiprotons and positrons produced there. This would be mining of the most exotic kind, extracting not rock or gas, but the inverse of substance itself. Yet a society this advanced would likely not rely solely on nature's meager production. They would become manufacturers on a scale that defies belief. Using a fraction of their stellar energy output, they could build orbital facilities dedicated solely to antimatter synthesis. These would be immense particle accelerators wrapped around calm, stable stars, using that star's power to drive collisions that churn out antimatter by the ton. One facility might produce enough in a year to fuel a voyage across the galaxy. A network of them could create strategic reserves large enough to power interstellar engineering projects for millennia. Mastering antimatter is about more than just accessing immense energy density. It is about asserting control over one of the universe's most fundamental symmetries. It means taming the most volatile reaction known to physics, bottling the power of annihilation itself, and turning it from a destructive force into a constructive tool. In a galaxy threaded with antimatter depots and fueled by annihilation drives, we would see the signature of a civilization that does not just use energy, but has learned to refine it into its purest, most potent form. This mastery of the particle realm suggests a final, inevitable evolution where energy is not merely consumed, but woven into the very purpose of existence. This immense journey unfolds across a timescale that makes human history feel like a single, fleeting breath. Reaching Type 3 status is not a project with a completion date. It is a slow, deliberate metamorphosis of a species and its environment, spanning millions or even billions of years. The path is not a straight line, but a series of evolutionary leaps, each one requiring the civilization to survive its own growing pains and the random violence of the cosmos. The first phase is one of profound consolidation. A species must master its home solar system completely, learning to harness every resource, stabilize every orbit, and protect its cradle from external threats. This alone could take millennia. Only from this position of absolute security can the next, more daring phase begin. The civilization would cast its gaze outward to the nearest stars. But sending ships with living crews across such voids is inefficient and slow. The tool for this stage is likely the von Neumann probe, a self-replicating robotic architect. A single probe is sent to a neighboring star system. It uses the local asteroids and comets to build copies of itself. Those copies then move on to the next stars and the next, creating an exponential wave of silent scouts. They are not colonists in the traditional sense. They are seeds planting the potential for infrastructure. They might begin by building simple communication relays, then energy collectors preparing the way. This wave of probes would spread at a significant fraction of light speed, but even so, crossing the vast spiral arms of a galaxy would take hundreds of thousands of years. The civilization would experience this expansion not as a rapid conquest, but as a gradual dawn slowly illuminating the map of their future home. As the wave front of probes moves outward, a slower, richer wave of integration would follow. This is when the civilization itself, in whatever form it now takes, begins to fill the prepared structures. Energy networks are activated, stellar management protocols begin. The galaxy is not conquered in a war, but inhabited through a process of careful, patient cultivation. This timescale introduces a staggering possibility. The civilization that begins this project and the one that completes it may be unrecognizable to each other. Over millions of years, a species will evolve. It will face existential filters, from the inevitable explosion of a nearby star to the internal risks of its own technology. Survival requires not just power, but profound wisdom and stability. The minds that eventually oversee a galactic network may have long since transitioned beyond the fragile biological forms that dreamed of the stars. They might exist as patterns of information within the very Dyson swarms they built, or as conscious currents in the quantum foam of their supercomputers. Their motivations, their art, their very sense of self would be as alien to us as our civilization would be to a single-celled organism drifting in an ancient sea. This contemplation does more than expand our sense of time. It reframes the entire concept of ambition. For us, a project lasting a century is a grand undertaking. For a civilization on this path, a million-year construction phase is simply the next logical step. Their planning horizon encompasses stellar lifetimes. Their patience is the patience of geology. Their resilience is the resilience of life itself, adapted not just to a planet, but to the galaxy. It highlights that the greatest challenge of cosmic survival may not be the engineering, but the sustained, coherent will to see it through across eons, to become something old and wise enough to hold a galaxy in steady hand. Even the mastery of antimatter might one day seem like a primitive step. Beyond the violent annihilation of particles lies a quieter, deeper ocean of potential, woven into the empty space between stars. This is the realm of quantum vacuum energy, often called zero-point energy, and it represents the final frontier in our speculative journey. According to quantum physics, what we perceive as a perfect vacuum is not truly empty. It is a seething, bubbling sea of virtual particles that wink in and out of existence in an endless dance governed by uncertainty. This activity gives every cubic centimeter of space a baseline energy, a hum of potential that is the lowest state a quantum field can have. For a Type 3 civilization, this concept presents a tantalizing, almost mythical possibility. What if you could tap not the objects in space, but the fabric of space itself? The energy density of this quantum vacuum is thought to be unimaginably vast, dwarfing even the combined output of every star in the galaxy. If a civilization could find a way to extract even a minuscule fraction of it, the implications would be revolutionary. Energy would cease to be something you harvest from specific locations like stars or black holes. It would become omnipresent, a utility as freely available as air. A starship would not need to carry fuel. It could draw power from the void it travels through. A megastructure would not need conduits from distant suns. It could power itself from the quantum fluctuations in its immediate vicinity. This is the dream of a truly physics-breaking technology, a power source utterly unconstrained by geography or resource depletion. Of course, our current understanding of physics throws immense cold water on this idea. Most theoretical models suggest that zero-point energy is fundamentally untappable, a constant background that cannot be used to perform work. It is like being surrounded by an ocean but having no bucket that can hold its water. The energy is locked away by the very laws that define it. Yet, this is precisely where we must stretch our imagination to encompass a civilization millions of years more advanced. Their breakthrough might not be in exploiting our known laws, but in discovering deeper layers of reality where what we see as a constant barrier is actually a malleable surface. They might have developed a technology to create a structured imbalance in the quantum foam, a kind of pressure differential in the fabric of spacetime that allows energy to flow into a usable form. Perhaps they could engineer exotic materials with properties that interact directly with these quantum fluctuations, acting as a sponge for the vacuum's latent power. While this remains firmly in the realm of speculation, the mere pursuit of such a frontier is deeply revealing. It illustrates a defining characteristic of a Type 3 civilization, boundless ingenuity driven by necessity. Having mastered every conventional energy source in its galaxy, it would inevitably turn its intellect toward the fundamental rules of the universe, seeking not just to use nature, but to gently negotiate with its underlying code. The quest for zero-point energy is less a practical engineering blueprint and more a symbol of an intelligence that never stops asking what else is possible, constantly pushing at the edges of reality to fuel its ascent. This relentless curiosity might be the most powerful engine of all. The galaxy, once a frontier, becomes a home, and from the quiet glow of a mastered Milky Way, a Type 3 civilization would inevitably cast its gaze beyond the local group into the profound darkness between islands of stars. The energy of a single galaxy, vast as it is, may one day become merely the foundation for a new, even grander ambition. The next logical step is not just to harvest a galaxy, but to connect it to others, weaving a web of power across the cosmic void. This is the dawn of intergalactic engineering, and it begins with a journey of almost unimaginable patience. The nearest large galaxy to our own, Andromeda, is 2.5 million light-years away. For a civilization thinking in million-year timescales, this is not an insurmountable barrier, but a profound logistical puzzle. The first emissaries would likely be the same self-replicating probes that once spread through the home galaxy, but now upgraded for an epic voyage. They would be launched in swarms, carrying the blueprints for Dyson swarms and stellar engines across the intergalactic sea. Their journey would be one of profound loneliness, coasting for millions of years through the near-perfect vacuum between galactic halos. Upon arrival in Andromeda, a single probe would awaken, find a resource-rich star system, and begin the slow, exponential process of replication and construction all over again. Over subsequent millions of years, a beachhead of captured stars would grow, a bubble of structured light in a foreign spiral arm. This would not be a colonial invasion, but a patient, automated process of infrastructure deployment, building power stations in a new stellar archipelago. Yet waiting millions of years for energy to flow back to the home galaxy is inefficient. This demands a more radical solution, one that bends the rules of space itself. The civilization might pursue the ultimate shortcut, the stable wormhole. While purely theoretical, the concept involves creating a tunnel through the folded fabric of space-time, connecting two distant points instantly. For energy transmission, this would be revolutionary. A wormhole terminus could be placed in the heart of the newly harvested Andromeda star cluster, with its other end resting in the Milky Way. The raw stellar energy could be pumped through this cosmic pipeline directly into the home grid, making the 2.5 million light-year distance irrelevant. The civilization would no longer be a master of one galaxy, but a custodian of a growing network, a nexus of power with tendrils reaching into the local group. This scale of project hints at a transition toward something even more staggering, a hypothetical Type 4 civilization. This entity would not think in terms of galaxies, but of the universe as a whole. Its energy budget would encompass the combined output of hundreds of billions of galaxies, the dark energy driving cosmic expansion, and perhaps the very quantum fires of the Big Bang. While a Type 3 civilization builds engines around stars, a Type 4 might contemplate engineering on a cosmological scale, perhaps seeking to influence the ultimate fate of the universe itself. This relentless drive to expand, to always seek the next greater source of power, reveals a deep and perhaps universal tension. It showcases the breathtaking potential of intelligence to rise from a single planet to shape the cosmos. Yet it also mirrors a pattern we know all too well, a tendency to grow and consume resources, now projected onto a canvas of galaxies and eons. It forces us to wonder if this expansion is an inevitable destiny for any mind that survives its technological adolescence, or if there is another path, one where mastery leads not to endless consumption, but to a state of equilibrium, wisdom, and perhaps even a conscious stewardship of the entire cosmic story. The silent darkness between galaxies may one day hum with the transmitted power of a connected universe, a testament to a will that refused to be bounded by anything, even the void. The very spin of a galaxy itself becomes a source of power. Every star, every wisp of gas, orbits the galactic core in a slow, majestic dance that has continued for billions of years. This collective motion represents an astronomical reservoir of kinetic energy, a river of momentum flowing on a scale that makes even supernovae seem like small events. A civilization that has mastered its stellar home would not overlook this. It would see the galaxy's rotation not just as a fact of nature, but as a colossal flywheel waiting to be tapped. The principle is elegant in its simplicity, though the engineering is anything but. To harvest this energy, you would need to create a form of galactic friction, a gentle brake applied to the spinning disk. One speculative method involves constructing titanic, static structures anchored in the galactic halo, the sparse outer region of the galaxy. These would be like the pylons of a cosmic dam, built to withstand forces beyond comprehension. Between them, vast dynamic nets or fields could be deployed, designed to interact with the passing flow of stars and interstellar gas. As the galaxy's spiral arms sweep through these stationary grids, the differential motion would be converted into usable power. It is the same principle as a tidal turbine in an ocean current, but here the current is made of suns, and the turbine is larger than a star cluster. The energy extracted comes directly from the galaxy's angular momentum, its spin. This means the process would, over eons, very gradually slow the galaxy's rotation. But for a civilization thinking in billion-year terms, this is not a flaw, it is a feature. The timescale is so vast that the deceleration would be imperceptible over even millions of years, a gentle nudging of cosmic mechanics rather than a violent halt. This harvesting would work in perfect harmony with the galaxy's innate motions, a subtle siphon placed in the river of time. It represents a holistic, almost serene approach to resource utilization. After mastering the fierce power of stars and black holes, a mature civilization might turn to this calmer, more systemic form of energy capture. It means viewing the galaxy not as a collection of discrete power plants, but as a single, integrated machine where every form of motion and potential energy is identified and harnessed. The radiant light of stars, the crushing gravity of singularities, and now the stately spin of the entire disk, all become threads in the same tapestry of power. This leaves no cosmic process unexploited, turning the galaxy's most fundamental behaviors into the steady heartbeat of civilization. A civilization that can reshape galaxies would be shaped by that power in return. Its social structure would be as alien and as vast as the engineering projects it commands, a reflection of minds that have evolved alongside stars. We can speculate on a few possible forms, each more staggering than the last. The first is unity, a single, galaxy-spanning consciousness. In this vision, the billions of Dyson swarms and Matrioshka brains are not separate computers but neurons in one colossal mind. The civilization ceases to be a collection of individuals. It becomes a unified field of thought, its awareness distributed across the light years, pondering questions that would take millennia for a signal to cross from one lobe to another. Disagreement, politics, and conflict as we know them would be relics of a biological past. This entity would have a single, coherent will, its purpose focused entirely on the maintenance of its galactic body and the pursuit of ultimate knowledge. It would be less a society and more a state of being, a galaxy that has woken up to think as one. Another possibility is a federation, a coalition of countless diverse intelligences. Perhaps the civilization began not with one species, but with many who learned to cooperate as they ascended the technological ladder. Or maybe, in its expansion across the stars, it encountered other forms of sapient life and incorporated them into a grand alliance. This galactic community would be a tapestry of different biologies, philosophies, and histories, united by shared technology and a common framework for existence. Their governance would have to operate on principles that transcend local biology, focusing on the management of the shared energy grid and the ethical stewardship of the galaxy. Vast virtual forums hosted in the computational layers of stars might allow for debates that last for centuries, as representatives from different spiral arms negotiate the fate of a nebula or the ethical guidelines for stellar mining. This structure celebrates diversity within a framework of unimaginable abundance. This abundance is the key to understanding daily life in such a realm. With the energy of billions of suns at its disposal, the civilization would exist in a state of absolute post-scarcity. The concept of lacking any material resource would be as absurd to them as a modern human worrying about a shortage of sticks to make fire. Everything from basic sustenance to the most complex megastructure components could be synthesized on demand by matter converters powered by the galactic grid. Work in the sense of labor for survival would not exist. Purpose would be decoupled from necessity. Beings, whether biological, synthetic, or something in between, would be free to pursue whatever gives their existence meaning. For some, this might mean dedicating an eternity to creating art on a stellar scale, sculpting nebulae with magnetic fields, or composing symphonies that use the pulsed light of variable stars as their notes. For others, it could mean pure exploration, not just of physical space, but of conceptual realms, mathematics, or simulated histories. The ultimate luxury in such a society would be attention and experience, the freedom to devote 1,000 years to mastering a single idea or to feeling the solar wind of 1,000,000 different stars. Yet the very scale that enables this paradise also contains the seeds of fragmentation. The Milky Way is over 100,000 light years across. Even with instantaneous communication via quantum links, the sheer physical and cultural distance between star clusters could lead to profound divergence over millions of years. One spiral arm specializing in black hole energy extraction might develop a culture of intense, focused engineering, viewing the universe as a system to be optimized. Another region, rich in stellar nurseries and biological preserves, might cultivate a philosophy of nurturing and growth, seeing the cosmos as a garden to be tended. Over eons, these branches of the same civilization could grow so distinct that they become separate entities, with only a tenuous connection through the ancient energy grid they all share. The galaxy might not host one civilization, but a family of them, each a unique interpretation of what it means to be intelligent amidst the stars. This social dimension is not a secondary detail. It is the very heart of the endeavor. The physics of stellar harvesting tells us what is possible. The sociology tells us why it would be done. A fragmented, warring galaxy would use its power for conquest and destruction, potentially tearing itself apart. A unified, compassionate consciousness might use that same power for creation and understanding, seeking to nurture life and unravel cosmic mysteries. The goals and ethics of the beings at the controls determine whether a galaxy becomes a gleaming engine of enlightenment or a dark, cold monument to control. It reminds us that technology, no matter how advanced, is always a tool. Its ultimate product is not energy, but the kind of universe the builders choose to make with it. The silent, structured light of a Dyson swarm does not tell us if the minds within are artists, philosophers, explorers, or something we have no words for. It only tells us that they are there and that they have chosen to build a home from starlight. Even the gentle hum of a spinning galaxy might one day feel like a quiet background note. For a civilization that has learned to listen to the universe with unimaginable sensitivity, the most powerful energy source may not be light or spin, but the very fabric of reality ringing like a bell. This is the frontier of gravitational wave energy capture, a concept that transforms the most violent cosmic collisions into a whisper of usable power. When two black holes, each millions of times heavier than our Sun, spiral inward and finally merge, they do not just release light, they shake the universe. Their immense masses, accelerating to nearly the speed of light in their final dance, create ripples in spacetime itself. These gravitational waves stretch and compress everything in their path, traveling outward at light speed, carrying with them a staggering amount of energy, often more than the combined light of every star in a galaxy for that brief, cataclysmic moment. We have only just begun to detect these whispers with instruments like LIGO, feeling the subtle tremors from events billions of light years away. For a Type 3 civilization, detection would be merely the first step. The next, almost inconceivable step would be to build a dam in that river of vibrating spacetime. The principle is one of resonance and damping. To harvest energy from any wave, you need something that can move in sync with it and then slow that motion down, converting the kinetic energy into another form. For an ocean wave, it is a buoy that rises and falls connected to a generator. For a gravitational wave, the equivalent would be a detector of unimaginable scale and sensitivity, designed not just to observe the ripple but to interact with it. One speculative idea involves creating a network of colossal, precisely balanced masses, perhaps entire planets or neutron stars, positioned light years apart across a star system. As a gravitational wave from a distant merger passes through, it would minutely change the distance between these masses. A civilization could use incredibly powerful magnetic fields or other forces to actively dampen the induced motion, essentially applying a gentle electronic brake to the ringing spacetime itself. The energy extracted from slowing that vibration could then be collected. The challenge is that gravitational waves, even from the most violent events, are incredibly diffuse by the time they reach any given point. The stretching of spacetime is minuscule, smaller than the width of an atom over a distance of millions of miles. Harvesting useful power from such a faint signal seems implausible. But this is where scale and patience redefine the possible. A single detector in one solar system might gather only a tiny trickle of energy from a passing wave. However, a civilization that has built a Dyson swarm around millions of stars has already created the perfect framework for a galaxy-spanning antenna array. Each managed star system could host its own gravitational wave dam. When a major merger event occurs anywhere in the galaxy, or even in a neighboring galaxy, the resulting wave would wash over this vast network simultaneously. Each node would contribute its minuscule harvest, and the collective energy, siphoned from the wave across billions of points, could add up to a significant pulse of power fed directly into the galactic grid. This method represents the ultimate form of turning cosmic lemons into lemonade. Supermassive black hole mergers and neutron star collisions are events of unimaginable destructive power, capable of sterilizing entire regions of space with their radiation. A lesser civilization would fear them or flee from them. A Type 3 civilization, having secured its infrastructure against such shocks, would see them as a resource. It would monitor the galaxy for impending mergers, perhaps even using its stellar shepherding techniques to gently nudge dangerous binaries toward a safe, harvestable collision course far from inhabited zones. The civilization would not just endure the universe's violence, it would schedule it, cushion the blow for its domains, and then plug into the aftershocks, drawing power from the ringing spacetime. This transforms our understanding of what energy harvesting means. It moves beyond capturing radiation from objects to tapping the dynamic geometry of the cosmos. It is the difference between collecting heat from a fire and harnessing the sound of the explosion that lit it. By seeking to dampen gravitational waves, a civilization demonstrates a mastery that goes beyond manipulating matter and energy. It shows an intent to calm the very tremors of creation, to smooth out the wrinkles in reality left by dying stars, and in doing so, to draw a quiet, relentless power from the symphony of cosmic catastrophe. The brilliant tapestry of a galaxy is woven with more than just stars. Between the blazing suns lie vast, dark reservoirs of potential, objects too cool to shine but still humming with immense internal energy. These are the brown dwarfs, the failed stars, and the gas giant planets, and for a thorough civilization, they represent a critical, untapped layer of the galactic power grid. A brown dwarf is a cosmic in-between, an object more massive than a planet like Jupiter, but not quite massive enough to sustain the core fusion that makes a true star shine. It forms from a collapsing cloud of gas, but its core never gets hot enough to ignite hydrogen. Instead, it glows faintly with a deep, ruddy heat, the leftover warmth from its violent birth and the slow, steady crush of gravity. For millions or billions of years, it simply cools in the darkness. To a civilization that can light stars, however, a brown dwarf is not a dead end. It is a pre-fueled furnace waiting for a spark. One audacious method of utilization would be stellar ignition. By artificially increasing the mass of a brown dwarf, perhaps by directing a carefully controlled stream of hydrogen siphoned from a nearby nebula into its core, the civilization could push it over the critical threshold. The increased pressure would finally trigger sustained hydrogen fusion, transforming the dark, cool object into a small, dim but genuine star. It would be the ultimate act of cosmic kindling, turning a smoldering ember into a controlled flame, adding a new, manageable point of light to the energy network. This is star building, the opposite of stellar mining, demonstrating an ability to not just harvest nature, but to gently correct its course, activating resources that the universe itself left dormant. Gas giant planets present a different but equally valuable opportunity. A world like Jupiter is not just a ball of gas, it is a deep well of raw fuel, primarily hydrogen, with a significant fraction of it in the form of a heavier isotope called deuterium. Deuterium is the gold standard for nuclear fusion reactions. It is easier to fuse than ordinary hydrogen and releases tremendous energy. Our oceans on Earth contain trace amounts of deuterium, but a gas giant's atmosphere holds oceans of it. A Type 3 civilization would not see Jupiter as a distant point of light. It would see it as a deuterium refinery the size of a world. The process of extraction would be industrial engineering on a planetary scale. Imagine vast, floating processing platforms suspended in the upper atmosphere of a gas giant, each one a city unto itself. These platforms would use powerful magnetic fields or chemical processes to filter and separate the deuterium from the vast seas of ordinary hydrogen, collecting it in immense storage tanks. Automated freighters, perhaps powered by the very fusion they enable, would then transport this precious fuel across the solar system to fusion reactors, or to antimatter production facilities, or to long-range starship depots. Every gas giant in every star system becomes a filling station for the galactic economy. its gravitational grip holding an almost inexhaustible supply of high-grade fusion fuel. This comprehensive utilization of brown dwarfs and gas giants completes the galactic energy picture. Bright stars provide the primary, luminous power. Black holes offer gravitational dynamos, but these darker, cooler objects fill in the gaps. They ensure that the energy web is not a sparse network connecting only the brightest points, but a dense, continuous fabric. In the vast voids between stellar systems, in the quiet outer reaches of galactic arms, brown dwarfs drift in darkness. By igniting them or tapping their internal heat, a civilization can plant power nodes in these empty territories, creating waste stations and infrastructure hubs where there was once only void. It eliminates dead zones in the energy grid. This approach exemplifies the thoroughness, the sheer diligence of a mature galactic intelligence. It is not enough to harvest the obvious, low-hanging fruit of Starlight. True mastery means ensuring that no significant mass, no potential energy gradient goes untapped. Every joule must be accounted for, every resource integrated into the system. It is the difference between a farmer who only cultivates the sunny hilltops and one who also terraces the slopes, irrigates the valleys, and enriches the soil everywhere, maximizing the yield of every single acre. By turning failed stars into successful ones and transforming planetary atmospheres into fuel depots, the civilization demonstrates that its vision is total. The galaxy is not a backdrop with a few useful features. It is a single, integrated machine, and every component, from the brightest quasar to the darkest, coldest dwarf, has a role to play in the grand, humming engine of civilization. The ultimate energy harvest may not be found in machines, but in the silent, green pulse of a leaf. Beyond the cold logic of Dyson swarms and black hole dynamos lies a parallel path, one where a civilization does not build its power grid from metal and light, but grows it from seed and cell. This is the realm of directed panspermia and bioenergy, a vision where technology and biology merge under the light of a billion suns. Here, engineering is not about construction, but about cultivation, transforming entire planets into living batteries or conscious gardens. It begins with a simple, profound act, the seeding of life. A civilization with mastery over genetics and interstellar travel could design resilient, hyper-efficient microorganisms or plant-like forms, engineered for one purpose: to convert a star's radiant energy into dense, storable biochemical energy with near-perfect efficiency. These tailored life forms would be packaged into durable capsules and fired like pollen across the galactic winds, aimed at every potentially habitable world within reach. Upon landing on a young planet with liquid water and a stable atmosphere, the seed awakens. It does not seek to build cities but to blanket continents. It grows not into a forest but into a single, planet-spanning organism, a photosynthetic mat of immense scale. Every leaf, every cell is a perfect solar collector, tuned to the specific spectrum of its local star. The organism's metabolism is designed not for reproduction or complexity, but for pure energy production and storage, perhaps creating vast underground reservoirs of rich hydrocarbons or complex sugars. The planet itself becomes a biological battery, slowly charging under its sun, its entire biosphere a unified engine for converting light into chemical potential. Periodically, automated harvesters would visit, gently collecting the accumulated energy stores without harming the living matrix, which simply continues its quiet work. This approach offers something pure machinery cannot: resilience and self-repair. If a meteor strikes or a solar flare scours the surface, the living network would regrow, healing itself according to its genetic programming. It adapts to gradual changes in planetary climate, evolving within its designed parameters to maintain peak efficiency. A galaxy cultivated in this way would present a breathtaking signature from afar. Instead of infrared heat from Dyson swarms, astronomers might detect planets with bizarrely uniform, intensely green biosignatures, worlds whose atmospheric chemistry screams of a single, purpose-driven biology covering every inch of their surface. But the biological ambition could reach even further into the realm of thought itself. Imagine if those planet-spanning organisms were not just energy converters, but neurons. Each living world, processing environmental data and internal states through its vast neural network-like root system, could become a single processing node. Link millions of such living planets via quantum entangled biological connections or subtle gravitational pulses, and you have the framework for a galactic brain, a consciousness literally rooted in worlds, its thoughts unfolding across the slow growth of continents and the seasonal cycles of entire atmospheres. This brain would not think in seconds but in geological epochs, its memories etched in fossil layers and its perceptions tuned to the gravitational music of orbiting stars. This biosymbiotic path represents a different philosophical choice for a galactic civilization. It is not about dominating nature with superior force, but about guiding it with a deeper understanding, creating a partnership between mind and life at a cosmic scale. The energy harvested is not merely a commodity, it is the product of a living universe being gently awakened to a new purpose. It asks whether the highest form of engineering is ultimately a form of gardening, and whether the most profound legacy a civilization can leave is not a galaxy of machines, but a galaxy that is itself alive and aware. This immense flow of power creates an equally immense problem, a byproduct that cannot be wished away. Every single conversion of energy, from starlight to electricity, from matter to motion, produces waste heat. It is the universe's most fundamental tax, enforced by the unbreakable laws of thermodynamics. For a civilization harvesting a galaxy, this is not a minor engineering footnote. It is an existential crisis on a cosmic scale. Picture all those billions of Dyson swarms. They capture the visible light of stars and convert it into useful work, but the process is never 100% efficient. The leftover energy, the waste, must be radiated away as lower-grade infrared heat. Now multiply that by every star in the galaxy. The collective glow of all this waste heat would be staggering, causing the entire galactic structure to shine with a fierce, unnatural warmth in the infrared spectrum. Astronomers call this signature a galactic infrared excess, and it would be a blazing beacon announcing a civilization's presence across the universe. But for the civilization itself, this heat is not a signal. It is a slow, creeping poison. Without a plan to manage it, the interior of the galaxy would begin to warm over millennia. The delicate balance of planetary climates, the operation of sensitive quantum computers, even the structural integrity of their megastructures, all depend on being able to dump heat into a cold sink. If the ambient temperature of the galaxy itself rises too high, that sink vanishes. They would face the ultimate irony, cooking their own civilization with the very energy they worked so hard to collect. So what can they do? The first and most direct solution is to become brilliant radiators. Their megastructures would be designed not just to capture energy, but to efficiently shed waste heat. This might involve building vast, wing-like structures on the dark sides of their Dyson swarms, panels specifically engineered to glow brightly in the infrared, pointing away from inhabited zones and out into the cold void of intergalactic space. They would essentially turn their galaxy into a directed heat lamp, aiming its waste glow into the emptiness between galaxies where it can dissipate harmlessly. But a more sophisticated approach would be to use the heat before discarding it. This is the principle of cascading efficiency, using waste not as a problem but as a lower-grade resource. The hottest waste from a primary reactor could power secondary industrial processes. The milder warmth from those could heat habitats or drive chemical synthesis. The last faint remnants of heat could be used for agriculture or to maintain ecological preserves. It would be a thermodynamic waterfall, extracting useful work at every step of the temperature decline until the final, useless trickle is finally radiated away. This relentless focus on heat management underscores a humbling and powerful truth. Even a civilization that moves stars and taps black holes cannot break the universe's core rules. The first law of thermodynamics says energy cannot be created or destroyed, only transformed. The second law says that in every transformation, some energy becomes unusable, increasing the disorder of the system. These are not suggestions, they are the bedrock framework of reality. A Type 3 civilization does not overcome these laws, it dances with them, mastering every possible step within the choreography they dictate. Their greatest engineering challenge is not generating power, but responsibly disposing of the universal tax that power generation demands. This confrontation with thermodynamic limits is what grounds our entire speculation in physical reality. It reminds us that even God-like powers operate within a system. The ultimate signature of intelligence may not be the scale of its constructions, but the elegance with which it navigates these fundamental constraints, turning the inevitable waste of creation into the foundation for a sustainable, eternal home. The silent glow of a Dyson swarm is only the beginning of the story, for every megastructure requires a physical body. To build a single energy collector the size of a continent, you need more steel, silicon, and rare earth elements than our entire planet could ever provide. To build billions of them, you must look beyond planets. You must learn to take a galaxy apart piece by piece and rebuild it into something new. The sheer mass required for a galactic civilization is the ultimate physical constraint, a mountain of matter so vast it makes the energy challenge seem simple by comparison. The numbers are once again astronomical. A single modest Dyson swarm, capturing just a fraction of a star's light, might require the dismantling of an entire planet like Mercury for its raw materials. To construct the full array of collectors, computers, and conduits across a galaxy, you would need the mass of millions, perhaps billions, of solar systems. No civilization, no matter how advanced, can create matter from nothing. They must become cosmic miners on a scale that redefines the word, turning asteroids, planets, and even stars themselves into quarries for their grand design. This begins with the low-hanging fruit of any solar system, the asteroid belt. These rocky remnants are perfect construction material, rich in metals and minerals, and they lack the troublesome gravity wells of planets. Early in their development, a civilization would deploy fleets of autonomous processors to these belts. These would not be mining drills and dump trucks as we know them. They would be swarms of molecular scale machines, nanotechnology, designed to disassemble asteroids atom by atom, sorting the iron, nickel, platinum, and silicon into pure streams of raw material. These streams would then be fed into orbital fabricators, vast 3D printers that use focused sunlight or particle beams to forge girders, solar panels, and circuit boards directly in the vacuum of space. An entire asteroid, kilometers across, could be consumed in a matter of months, transformed from a lump of rock into a gleaming, functional segment of a Dyson swarm. But asteroids are merely the appetizer. To build at a galactic pace, you need planetary scale resources. This leads to a process of profound transformation, planetary disassembly. A civilization might select a lifeless, metal-rich world, or even a gas giant's moons, and begin the slow, methodical work of taking it apart. One method could involve using colossal gravity manipulators, devices that create targeted tidal forces to gently pull the planet apart into manageable rings of debris, like peeling the layers of a cosmic onion. Another might involve drilling to the core to trigger controlled volcanic activity, bringing deep mantle material to the surface for easy collection. Over centuries, a world would vanish, its entire mass converted into a cloud of processed material orbiting its star, a ready-made warehouse for the construction projects to come. Yet even consuming every rocky planet in 1,000 systems is not enough. The final frontier of material sourcing is the star itself. Stellar lifting, the process of skimming plasma from a sun, provides not just fuel but raw atoms. A star is a giant ball of hydrogen and helium, but within its churning heart, nuclear fusion forges heavier elements: carbon, oxygen, silicon, and iron. By carefully processing the siphoned stellar material, a civilization could extract these precious metals, the very building blocks of technology, directly from the furnace that created them. This represents the closing of a magnificent industrial loop. You use the star's energy to power the machines that mine the star for the materials to build more machines to capture more of the star's energy. The star becomes both engine and ore, a self-contained industrial hub. The logistics of moving this unimaginable tonnage across light years then becomes the next great challenge. You cannot simply load asteroids onto freighters. The energy cost would be absurd. Instead, material would likely be converted into a more transportable form. One speculative idea is to transmute bulk matter into a plasma stream, which is then magnetically accelerated along pre-established routes between stars, like a pipeline of raw atoms flowing through the void. At the destination, the stream is cooled and re-solidified into whatever structure is needed. Another method might involve converting matter into pure information, transmitting the atomic blueprint of a megastructure component via quantum entanglement to a receiver station that uses local, generic matter to assemble it according to the instructions. This would be the ultimate form of teleportation for industry, sending the idea of an object rather than the object itself. This relentless, galaxy-spanning harvest would leave indelible marks on the cosmos. As a civilization expands, it would create vast, mapped regions where every usable asteroid, every accessible planet, and every manageable star has been processed. From a great distance, these zones might appear as strange voids within the galactic disk, areas curiously depleted of the natural clutter of solar systems, their stars shining with artificial clarity against an unnaturally clean backdrop. In their wake, they might leave trails of refined waste, slag from industrial processing formed into immense crystalline structures or scattered as faint, metallic dust clouds that drift between the stars, catching the light in unusual ways. The galaxy's very composition would change over eons, as heavy elements are systematically gathered from their natural dispersal and concentrated into the organized matrices of civilization. This reshapes our understanding of what we might be looking for. The signature of intelligence may not always be a glow of light. It could be a puzzling absence, a region of space that is too clean, too orderly, where the expected debris of cosmic evolution has been meticulously cleared away. It suggests that a mature galactic society is not just a consumer of energy, but a voracious organizer of matter, leaving behind a legacy not of monuments, but of emptiness, a quiet testament to the fact that everything that was once there has been taken up and put to use in a design far greater than nature alone could ever muster. The sheer size of a galaxy makes our most advanced networks look like a child's string telephone. Managing a project across hundreds of thousands of light years presents a fundamental paradox. How do you coordinate actions when a simple question and answer could take longer than all of recorded human history? The speed of light, the universe's ultimate speed limit, is not just a barrier for travel, it is a barrier for conversation. A civilization cannot run a galaxy with memos that take millennia to arrive. It must either find a way to communicate instantly, or it must design a society that does not need to. One theoretical and deeply controversial possibility is the quantum network. If particles can be entangled across vast distances, their linked states changing in perfect unison, then perhaps they could be used as a kind of cosmic telegraph. You would not send energy or matter through this link, but you could send a perfectly synchronized signal, a single bit of yes or no, on or off, that appears simultaneously at both ends. Imagine two construction sites, each orbiting a star 50,000 light-years apart. They each hold one half of an entangled particle pair. When the engineers at the first site finish a critical phase, they manipulate their particle in a specific way. Instantly, without any delay, the particle at the second site changes, triggering the next phase of construction there. It is not a phone call, it is a shared heartbeat. This would allow for perfect synchronization of events across the void, creating a unified rhythm for projects that span the galactic disk. Yet this is a fragile, exotic solution, likely reserved for only the most critical of commands. For the vast daily flow of data, the civilization would use the galaxy itself as its network. They could modulate the output of their Dyson swarms, creating intricate pulses in the infrared waste heat or in the directed energy beams that crisscross the void. A star's light, once a steady beacon, could be made to flicker in complex mathematical patterns. To an outside observer, it might look like a variable star with an impossibly precise rhythm. To the civilization, it is a data packet carrying updates on resource levels, engineering schematics, or even cultural archives, broadcast from one star system to its neighbors, who receive it, amplify it, and pass it along. The entire galaxy becomes a vast, slow internet, with Starlight as its carrier signal. But the most robust solution may be to eliminate the need for constant conversation altogether. This is the realm of autonomous intelligence. The civilization would not send detailed instructions to its probes and construction swarms. It would send seeds of purpose. A von Neumann probe arrives in a new system not with a blueprint, but with a set of high-level goals and the creative intelligence to achieve them. It is told to harvest energy, to build infrastructure, to seek out resources, and to replicate when necessary, but it is given the freedom to solve those problems based on local conditions. It becomes a partner, not a puppet. Over millions of years, these autonomous agents spread across the spiral arms would develop their own local cultures of problem-solving, adapting to the unique challenges of the galactic core, the sparse halo, or the turbulent stellar nurseries. They would share innovations not by asking for permission, but by broadcasting their successes for others to adopt if they find them useful. This leads to a social structure unlike anything we know. A central government issuing orders from a capital world is impossible when the capital's latest decree would be ancient history by the time it reached the outer arms. Instead, the civilization would evolve into something more like a hive mind, but not in the creepy, monolithic sense. Think of it as a consensus intelligence. Each node, each star system with its own local AI, and perhaps its own community of beings, operates with a high degree of independence. But they are all united by a shared foundational protocol, a common set of ethical principles and overarching goals, like the constitution of a galaxy. Their cohesion comes not from taking orders, but from sharing a vision so deeply ingrained it feels like instinct. They coordinate through a constant, slow exchange of data and cultural artifacts, a galactic conversation that unfolds over epochs, allowing best practices and new ideas to diffuse across the vast network at the speed of light. This creates a society of incredible resilience. If a supernova wipes out a sector, or if a segment of the network goes silent for 100,000 years, the rest of the civilization continues. There is no single point of failure, no head to cut off. The project of galactic cultivation becomes a distributed, self-healing process. The proof of their coordination is not in a chain of command, but in the harmonious result. The energy siphoned from a red giant in one spiral arm arrives precisely when it is needed to power the delicate stellar ignition of a brown dwarf in another. The flow of raw materials from dismantled asteroids follows routes that are constantly optimized by 1 trillion autonomous agents, all working toward the common good of the whole. They achieve this not because they were told to, but because their very design, their shared purpose, compels them to seek this elegant, efficient balance. It is a testament to organizational prowess that transcends management. It is the emergence of a galactic scale mind, not as a single thinker, but as a symphony of countless intelligences, all playing the same grand million-year song, each from their own lonely corner of the stage. The universe is a very big place, but it is not infinite. If intelligence is a natural outcome of cosmic evolution, then other minds must have risen to the same staggering heights. And if they have, then the silent, structured galaxies we imagine might not be isolated gardens. They could be neighboring empires, separated by gulfs of time and space so vast we cannot fathom them, yet destined one day to meet. This introduces a possibility far removed from serene contemplation, the risk of galactic conflict. In a cosmos where civilizations command the power of stars, a simple misunderstanding, a clash of values, or competition over the last untapped galaxy could escalate into a war unlike any other. This would not be a conflict of soldiers and tanks. It would be a war of astrophysics, fought with tools that reshape reality itself. The very energy-harvesting infrastructure we have described, the Dyson swarms and stellar engines, could be repurposed in an instant. A network designed to beam power to construction sites could focus that same energy into a weapon of unimaginable intensity, a laser capable of boiling away a planet's atmosphere from across a star system. A Kadov thruster built to gently shepherd a star could be turned into a cannon, accelerating that star to a significant fraction of light speed and aiming it like a colossal bullet at an enemy's core worlds. The black hole bomb, conceived as a power generator, could be overloaded, releasing its amplified energy in a single, catastrophic burst meant to sterilize an entire spiral arm. In such a conflict, space-time itself becomes the battlefield. A civilization might learn to generate controlled gravitational waves, not to harvest energy, but to create destructive resonances that shake enemy megastructures apart at the atomic level. They could attempt to induce false vacuum decay, a theoretical catastrophe where a bubble of fundamentally altered physics expands at light speed, rewriting the laws of the universe in its wake and erasing the enemy from existence. The scale of destruction is so complete it becomes philosophical, a battle not for territory, but for the right to dictate which version of reality gets to continue. This grim potential adds a profound layer of strategic complexity to the drive for energy mastery. For a Type 3 civilization, energy security is not just about fueling growth, it becomes synonymous with survival. The relentless harvest of Starlight might be driven as much by deterrence as by curiosity. A galaxy fully converted into a power grid is not just a home, it is a fortress. Its immense, focused energy output could power planetary-scale shields, create sensor networks that see across intergalactic space, and maintain fleets of autonomous defensive probes. The civilization becomes a porcupine of cosmic proportions, its quills made of directed starlight and its hide woven from manipulated gravity. The motivation to expand, to harvest every last jewel from every brown dwarf and nebula, could be fueled by a simple, chilling calculus. In a potentially crowded and competitive cosmos, the civilization that controls the most energy controls its own destiny. It can outlast, outbuild, and outthink any rival. It can afford the energy cost of perfect simulations to predict an adversary's moves millennia in advance. It can afford to waste entire stars as decoys or as fuel for emergency faster than light retreats. This perspective transforms our understanding of their grand projects. That mysterious infrared glow of a galaxy might not be the waste heat of peaceful computation. It could be the idle hum of a war machine in stand-by mode, a galaxy kept perpetually ready, its billions of suns poised to focus their fury at a moment's notice. The eerie silence of the cosmos, the fact that we see no obvious signs of such titanic engineering, takes on a new and unsettling meaning. It might be that civilizations which reach this apex of power understand the stakes too well. They know that any detectable signature is a potential target, so they cloak their activities, masking their infrared excess behind shells of cooled matter or dispersing their waste heat in ways indistinguishable from natural phenomena. They become cosmic ghosts, masters of stealth on a galactic scale, because to reveal yourself is to invite a conflict that could end not just your civilization, but your entire galactic neighborhood. This introduces a possible answer to the Fermi paradox, the question of where everybody is. They are not missing. They are hiding, carefully managing their energy signatures behind a veil of perfect operational security, listening intently into the darkness, hoping never to hear an echo of another mind like their own. In such a universe, the ultimate achievement of a Type 3 civilization may not be how much energy it harvests, but how well it conceals the fact that it is harvesting anything at all. But even a galaxy woven with light-speed data streams is still constrained by the most fundamental rule of all. The universe's ultimate speed limit creates a problem of scale no amount of engineering can fully solve with conventional means. For a civilization that thinks in unified terms, the vast gulfs between its power stations and cities would feel like a flaw in the design, a lag in the system that prevents true, instantaneous cohesion. To achieve perfect control, they would need to bend the rules or perhaps find the rules that allow for bending. This draws their ambition toward two of the most speculative concepts in all of physics, wormholes and cosmic strings, technologies that would not just use space but reshape its very geometry. The dream of the wormhole is the dream of a shortcut. In theory, it is a tunnel, a bridge connecting two distant points in spacetime, folded together so that a journey through the tunnel is instantaneous while the outside distance remains immense. For a Type 3 civilization, this is not merely a tool for exploration. It is the ultimate utility for energy management. Imagine a stable wormhole, its one mouth positioned in the furious accretion disk of the supermassive black hole at the galactic center, where power generation is at its peak. The other mouth could be placed in a quiet research station in a distant, resource-poor spiral arm. Instead of beaming energy across tens of thousands of light-years, losing power and facing millennia of delay, the raw, titanic output of the core could flow directly through this cosmic pipeline. The station would have a direct, real-time tap into the galaxy's main generator. This transforms the energy grid from a network of slow beams into a web of instantaneous connections. A star-going supernova in one sector could have its final, cataclysmic energy surge diverted through a wormhole to fuel a stellar ignition project on the far side of the galaxy, all in the blink of an eye. The civilization could balance its energy budget across the entire galactic disk as easily as we adjust the thermostat in a single house. Yet wormholes, if they can exist at all, are notoriously unstable. Theoretical models suggest they would collapse instantly unless held open by something with negative energy density, a form of exotic matter that pushes rather than pulls. The quest to create and stabilize a wormhole would therefore be one of the civilization's ultimate physics experiments. It would involve not just grand engineering, but a deep manipulation of quantum fields, perhaps learning to structure the vacuum of space itself into a shape that remains open. Success would mean mastering a fundamental aspect of reality, turning a mathematical curiosity into a foundational piece of infrastructure. Each stable wormhole would be a monument to their understanding, a stitch in the fabric of the cosmos that binds their domain together. Then there is the even more enigmatic concept of cosmic strings. These are not objects in space, but flaws in spacetime. theorized as ultra-dense, one-dimensional defects left over from the universe's earliest, most violent moments. A cosmic string would be a filament of pure distortion, thinner than an atom, but with the mass of a mountain range packed into every inch. Its gravitational influence would be bizarre, acting like a lens that distorts the light of anything behind it. For a civilization with the ability to locate and manipulate such an entity, the possibilities are staggering. A cosmic string under tension vibrates, and those vibrations could be a source of colossal energy, a fundamental hum of the universe that could be tapped. But its greater value might be in its unique geometry. The spacetime around a cosmic string is not simply curved, it is looped in a way that, in theory, could allow for closed time-like curves, the basis for theoretical time travel, or more practically, for creating stable corridors where normal rules of distance break down. Harnessing a cosmic string would be an act of cosmic archaeology and high-stakes engineering combined. The civilization would first have to map the galaxy for these ancient scars, tracing their influence by the strange, double images of distant galaxies they create. Once found, they would need to somehow anchor it, to dampen its natural vibrations and integrate it into their network. Aligning a series of wormhole mouths along the length of a stabilized cosmic string could create a backbone, a superhighway of instantaneous transfer that runs through the heart of the galaxy. Energy, information, and even physical probes could move along this spine, leaping from point to point via the connected wormholes, making the entire structure a unified nervous system. The galaxy would no longer be a flat disk with vast distances, but a folded origami where every point is a crease away from every other point. The pursuit of these technologies represents the final phase of optimization, where a civilization moves from managing resources within space to managing the structure of space itself. It is the difference between building roads across a continent and learning to fold the continent so that every city shares a border. While these ideas dwell at the very edge of our current physics, their pursuit is a logical endpoint for a mind that refuses to accept distance as a limit. A civilization that stitches its galaxy together with wormholes and cosmic strings is not just building a home, it is performing delicate surgery on the universe, healing the perceived flaw of separation and weaving a scattered collection of stars into a single, seamless, and intelligently designed whole. In such a galaxy, the very idea of loneliness would be obsolete. For every star, every outpost, every mind would be intimately and instantly connected to the vibrant, humming heart of the entire creation. Yet all this power must serve a purpose far greater than mere survival. A civilization that has woven starlight into its veins is no longer asking how to live, but why. What transcendent goal could possibly demand the energy of an entire galaxy? The answer may lie in the ultimate act of creation, the simulation of reality itself. With a computational power of 1 billion Matrioshka brains, such a society could run hyper-detailed models of entire universes, tracing every particle from a simulated Big Bang forward through billions of virtual years. These would not be simple video games, but fully realized, self-consistent realities, perhaps populated by conscious digital minds. The energy required to sustain such an intricate, dynamic cosmos would be astronomical, a fitting expenditure for a civilization playing at being gods, not out of arrogance, but out of a profound desire to understand the nature of existence, causality, and life. It would be the final experiment, a laboratory for exploring every possible path of cosmic evolution, including their own. Alternatively, that immense energy could fuel the most ambitious journey imaginable, an exodus from their home galaxy. The local group of galaxies is destined to merge over billions of years, but a Type 3 civilization might not want to wait. They could use their harvested power to enact a controlled, accelerated expansion, turning their galactic infrastructure into a single, titanic generation ship. By carefully manipulating gravity and inertia, they might gently move the entire Milky Way, or at least its most vital stellar components, on a voyage to another galactic cluster, seeking new resources, new cosmic vistas, or even contact with other intelligences. The energy to nudge billions of stars onto a new course would dwarf even the power needed to hold them in place. A project of such scale, it redefines the concept of exploration. Perhaps the most profound goal is not expansion but preservation, a fight against the universe's most inevitable law. Entropy, the slow and steady trend toward disorder and heat death, is the ultimate enemy of all complex structures, including life and thought. A civilization at this level might attempt to create localized reversals of entropy, establishing pockets of perfect order amidst the cosmic decay. They could use their energy to constantly reorder disordered systems, repair information loss, and maintain islands of structure and consciousness indefinitely. This is not about achieving immortality for individuals, but about securing a permanent foothold for mind in a universe sliding toward silent equilibrium. It is the ultimate act of cosmic stewardship, using a galaxy's power to tend a fragile garden of complexity against the entropic tide. This energy could also be the ultimate tool for artistic and scientific expression on a scale we cannot fathom. Imagine dedicating the light of 1,000,000 stars to a single, ephemeral sculpture of magnetically confined plasma, a temporary artwork larger than a nebula that tells a story to anyone watching from 1,000 light-years away. Or consider the energy demands of a physics experiment that probes the conditions of the first trillionth of a second after the Big Bang, requiring the concentration of galactic power into a volume smaller than an atom for a fleeting instant. The pursuit of pure beauty and pure knowledge, unrestrained by any resource limit, becomes a valid and overwhelming driver for such a society. Ultimately, these staggering motivations suggest that a Type 3 civilization's energy hunger is not mindless consumption. It is the logical extension of curiosity, creativity, and the will to persist. The power of a galaxy becomes the brush for painting on the canvas of the cosmos, the fuel for a voyage without end, or the shield against the final darkness. Their projects are not about having more, but about being more, about leveraging the raw stuff of stars to answer the oldest and deepest questions any mind can ask. What is our place in the universe? What can we create? And how long can we, and the things we value, endure? The silent, restructured light of their galaxy is not just a signature of their technology, but a testament to their purpose, a beacon declaring that in this corner of the cosmos, intelligence found a way to turn survival into meaning. The brilliant, restructured galaxy we have been envisioning is nowhere to be seen. Our telescopes scan the cosmos, finding only the natural, chaotic glow of billions of untended suns. This profound silence is not just an empty observation. It is a puzzle that cuts to the very heart of our speculation, a question so sharp it has a name, the Fermi paradox. If the universe is so vast and so old, and if intelligent life is a natural outcome, then the cosmos should be teeming with civilizations, including those of Type 3. Their megastructures should be visible across the void, yet we look up and see nothing but ancient starlight. Where is everybody? This paradox is the ultimate reality check for our grand visions, forcing us to confront the gap between what seems possible and what we actually observe. The silence is not a dead end, however. It is a guide pointing us toward several profound and sometimes unsettling possibilities. The first and simplest answer is that they are simply very, very rare. The path from a single-celled organism to a galaxy-spanning intelligence might be littered with obstacles far greater than we realize. Perhaps the leap to sustainable planetary civilization is a filter that almost no species passes. Or maybe the technological adolescence of harnessing atomic energy and artificial intelligence is a cliff that most civilizations fall from. In this view, The cosmos is not a crowded metropolis, but a scattering of isolated islands where life flickers briefly before going dark. We might be alone in our galactic neighborhood, or among the first to reach this point in a universe still too young for others to have made the journey. Another possibility is not that they are absent, but that they have transformed into something we cannot recognize. Our entire search is based on looking for things like us, beings that build physical machines and radiate waste heat. But what if a mature civilization evolves beyond that? After millions of years, they might transition into a state of pure information, existing as patterns of consciousness within the quantum fields of space itself, or within simulated realities running on Matrioshka brains. Their presence would not be marked by the infrared glow of Dyson swarms, but by subtle gravitational anomalies or strange patterns in the cosmic microwave background, signatures we lack the physics or the perspective to even identify. They are not hiding, they have simply graduated to a form of existence that operates on rules we have yet to discover. Then there is the more strategic explanation, the concept of deliberate stealth. In a universe that might contain other, potentially hostile intelligences, broadcasting your location with a galaxy-sized beacon of waste heat would be the ultimate folly. A wise, ancient civilization would have learned to cloak its activities. They could engineer their Dyson swarms to radiate heat in a directed, narrow beam aimed into intergalactic space, or they might use advanced thermodynamics to recycle virtually all waste energy internally, leaving only a faint, natural-looking signature. Their entire galactic infrastructure could be designed for minimal observable impact, a practice of cosmic camouflage born from a deep understanding of survival in a potentially dangerous cosmos. Our discussion of harvesting methods directly informs this idea of subtlety. We assumed a civilization would need to build obvious, glowing structures. But what if their energy collection is so profoundly efficient it borders on the undetectable? Imagine they have mastered the direct conversion of stellar plasma into usable work with near-perfect efficiency, or they tap the quantum vacuum, drawing power from empty space with no thermal byproduct at all. Their technology might not operate in the visible light spectrum at all, but in realms of physics we are only beginning to glimpse, using dark matter interactions or gravitational manipulation. To our instruments, their home galaxy would look perfectly normal, a serene spiral of stars, while beneath that placid surface, a titanic civilization hums with activity, invisible by design. This leads to the final, humbling branch of the paradox. Perhaps they are here, and we are just not looking correctly. Our searches are in their infancy. We have scanned for radio signals for less than a century, and for infrared excesses in only a tiny fraction of galaxies. A galactic civilization's signature might be a slow, subtle modulation in a star's light over millennia, a pattern our brief observations would never catch. Or their communication might be in a medium we ignore, like modulated neutrino streams or quantum-entangled particle states. We are like someone searching for evidence of a global internet by only listening for the hum of power lines, missing the invisible data flowing through the air all around us. Grappling with the Fermi paradox does not invalidate our speculation. It grounds it. It forces us to refine our models, to think more creatively about what advanced intelligence might look like, and to be more precise in our search of the heavens. The paradox is a challenge, a reminder that the universe is under no obligation to conform to our expectations. The great silence may be a message in itself, telling us that the next great discovery in astronomy will not be a new star or a new planet, but a new way of seeing. It pushes us to ask not just how a civilization would harvest a galaxy, but how it would choose to reveal itself, or if it would choose to reveal itself at all. In the quiet between the stars, the answer is waiting, not in what we see, but in what we have yet to learn how to look for. Our own civilization, for all its dazzling achievements, currently sits at a mere 0.7 on the Kardashev scale. We have not yet unified our planetary energy systems, let alone touched the power of our Sun. Against the backdrop of galactic harvesters and stellar architects, we are still learning to light our own small campfire in a universe of infernos. Yet this vast disparity is not a cause for despair, but for perspective. Contemplating these far future possibilities does something profound for us here and now. It stretches our imagination across time scales usually reserved for geology and astronomy, forcing us to think in terms of centuries, millennia, and epochs, rather than quarterly reports or election cycles. It asks us to consider what kind of legacy we wish to build, not for the next generation, but for a potential lineage of intelligence that might one day look back at this moment as its distant, mythic origin. This long-term view is the ultimate antidote to short-sightedness. Every decision we make about our technology, our environment, and our cooperation as a species can be seen as a foundational step. Are we laying the groundwork for a stable, wise Type 1 civilization that manages its planet with care, or are we creating patterns of conflict and waste that will limit our future before it even begins? The ethics we develop today regarding artificial intelligence, genetic engineering, and resource sharing are not just policy debates. They are the first drafts of the operating principles for a society that might one day need to decide whether to ignite a brown dwarf or preserve a nebula teeming with prebiotic chemistry. Our current technological adolescence is the most dangerous phase we will ever face, precisely because we wield great power without the corresponding wisdom or security of a fully mature civilization. Navigating this precarious stage requires a blend of bold ambition and profound humility. The ambition to reach for the stars, to solve grand challenges, and to elevate our understanding of the cosmos. The humility to recognize our fragility, to protect our only home, and to approach new powers with caution and foresight. This balance is the great work of our time. To daydream of Dyson spheres is easy. The harder, more essential task is to master sustainable fusion, to heal our biosphere, and to forge a global identity that transcends ancient divisions. These are the practical, gritty prerequisites for any dream of galactic destiny. In this way, the Type 3 thought experiment serves as a powerful mirror. It reflects our deepest hopes for transcendence and our fears of self-destruction. It channels our innate curiosity about the universe and our place within it into a narrative of incredible scale. The silence we hear from the cosmos, the Fermi paradox, whispers a cautionary tale. It suggests that the great filter, the obstacle that prevents life from reaching the stars, might not be ahead of us in the vast dark. It might be right here, right now, in this delicate transition we are currently navigating. Our success is not guaranteed, but neither is our failure. This perspective ultimately enriches our present moment. When you look up at the night sky, you are no longer just seeing points of light. You are seeing potential homes, future engines, and unanswered questions. You are witnessing a cosmic story in which we have just begun to write the opening paragraph. Our current flicker of consciousness, brief as it may be against the backdrop of galactic time, is the spark from which an entire universe of possibility could yet be kindled. Whether that spark catches fire or winks out quietly in the dark is a story still being written by us, here and now, with every choice we make. The journey we have taken across these ideas is not just a tour of possible technologies. It is a map of a mind expanding to fit the cosmos. From the simple, elegant concept of the Kardashev scale, we have ventured into the realms of stellar minds and black hole dynamos, of self-replicating probes and galaxy-spanning power grids. We have stood before the ethical mirror of cosmic stewardship and peered into the profound silence of the Fermi paradox, asking what our place in this grand story might be. These visions, while rooted in the edges of known physics, serve a purpose far greater than prediction. They stretch the fabric of our imagination. They force us to think not in years or centuries, but in galactic epochs, to see intelligence not as a fleeting moment on a single world, but as a potential force of nature, as fundamental to a galaxy's future as gravity or light. This expansion of perspective is perhaps their greatest gift to us here now, in our own fragile moment of awakening. It challenges us to consider the legacy we are building with every step we take into our own technological future. If this exploration of cosmic potential resonated with you, I would be deeply grateful if you would like this video and subscribe to the channel. Your support fuels these deep dives into the mysteries of space. And I am truly curious to hear your perspective in the comments below. After considering all these staggering methods, from Dyson swarms to zero-point energy, which one feels the most plausible or compelling to you as a path a future civilization might take? Thank you so much for joining me on this journey through the ultimate limits of energy and imagination. Until next time, keep looking up and never stop wondering what might be possible.